Welcome to the Bedtime Lab, my dear friend. Here, we're all about easing you into a restful sleep while sharing fascinating tidbits of knowledge. Tonight, we're diving into the captivating realm of neutron stars and pulsars, celestial wonders that sparkle with mystery and intrigue. Before we delve deeper, I invite you to comment where you're from. It's lovely to know where our friends are listening from around the globe. Now, let me share something interesting with you. Imagine a star that has exhausted its nuclear fuel and collapsed under the weight of its own gravity. This is how a neutron star is born, an incredibly dense object where a single teaspoonful would weigh around 6 billion tons. Can you imagine such immense density? Speaking of density, did you know that neutron stars are so compact that they could fit into a city the size of Chicago? Yet, they possess a mass that can be twice that of our Sun. It's like squeezing the Sun into a sphere only 20 kilometers in diameter. Here's a fascinating fact. The gravity on the surface of a neutron star is about 2 billion times stronger than gravity here on Earth. If you were to venture close to one, the gravitational pull would be so intense that it would stretch and thin you out like spaghetti. This phenomenon even has a playful name, spaghettification. And here's something awe-inspiring. Neutron stars rotate at incredible speeds. Some spin several hundred times per second. These rapidly rotating neutron stars are known as pulsars, and they emit beams of electromagnetic radiation that sweep across space like cosmic lighthouses. It's mesmerizing to think about, isn't it? Speaking of pulsars, did you know the first one was discovered quite by accident in 1967 by a graduate student named Jocelyn Bell Burnell? She noticed a strange, regular pulsing signal that she initially thought might be little green men trying to communicate. It turned out to be the discovery of the very first pulsar, which was an extraordinary breakthrough in astronomy. Here's another curious fact. The fastest known spinning neutron star, known as PSR Jones 748-2446 AD, rotates at a breathtaking rate of 716 times per second. Just try to picture something spinning that fast. It's a bit dizzying, isn't it? Now, speaking of fast rotations, let me tell you about magnetars. They are a type of neutron star with an incredibly strong magnetic field, up to 1,000 times stronger than that of a typical neutron star. This magnetic field is so powerful that if a magnetar was situated halfway between the Earth and the Moon, it could wipe all credit card data on Earth. It's a gentle reminder of the immense forces at play in our universe. And here's an intriguing thought. Neutron stars can have a surface temperature of roughly 1 million degrees Celsius. Yet, despite this intense heat, they appear quite dim in visible light because they're so small. They do emit copious amounts of X-rays, though, which astronomers can detect with special telescopes. Did you know that the collision of two neutron stars can create heavy elements like gold and platinum? These cosmic events, known as kilonovae, release such incredible amounts of energy that they can outshine an entire galaxy for a short period. Next time you wear a piece of gold jewelry, just imagine it might have originated from a spectacular cosmic collision. And speaking of cosmic events, have you ever wondered about the role of neutron stars in gravitational waves? When two neutron stars orbit each other closely and eventually collide, they send ripples across the fabric of space-time, which we observe as gravitational waves. These waves were first detected in 2017, confirming yet another prediction of Einstein's general theory of relativity. Here's a delightful detail for you. Some neutron stars in binary systems can pull material from a companion star. This process can cause them to flare up dramatically, in what's known as an X-ray burst, a sudden and intense release of X-ray radiation. It's a cosmic tango between two stars, dancing in the vastness of space.
And let me add one more captivating fact.
Neutron stars can host fluctuations on their surfaces called starquakes, which are similar to earthquakes here on Earth. These starquakes can cause sudden changes in the rotation of the star, leading to tiny disruptions in the rotation of the star, leading to tiny disruptions in the regular pulsing of pulsars, which are detected as glitches. Reflecting on all these wondrous phenomena, it's astonishing to think about the secrets the universe holds and how much we still have to discover. Neutron stars and pulsars remind us of the universe's extraordinary power and beauty. As you drift off to sleep tonight, let your imagination wander among the stars, knowing that each one has its own story to tell, waiting to be uncovered and shared. Until next time, sweet dreams. As you continue to settle into a cozy state of calm, let me take you on a further journey into the mesmerizing world of neutron stars and pulsars. These celestial entities are full of surprises, each more astonishing than the last. Did you know that neutron stars are capable of generating powerful winds of particles that stream outwards at nearly the speed of light? These winds create an astonishing display of energy and are a key ingredient in the formation of pulsar wind nebulae, beautiful clouds of particles that glow in dazzling light. It's like having a cosmic fireworks show right in the depths of space. Speaking of remarkable phenomena, let's consider the fascinating fact that some neutron stars exhibit a peculiar property known as precession. Much like a spinning top wobbling as it slows down, these stars experience a slow gyration of their rotational axis. This can lead to changes in the timing of their pulses, presenting a unique challenge and opportunity for astronomers who study these mysterious objects. And here's an intriguing thought. The crust of a neutron star is thought to be incredibly hard, possibly the strongest known material in the universe. This nuclear pasta, as scientists whimsically call it, can resist immensely high pressures without breaking. Imagine a structure so tough that it defies your ordinary understanding of matter. Let's talk about something even more mind-bending. Inside a neutron star, the density is so extreme that the atomic nuclei are crushed together, creating an environment where exotic particles like pions and kaons might exist. These particles are not typically found on Earth, opening a window into physics under conditions we cannot replicate in any laboratory. It's a true testament to the vast and mysterious capabilities of the universe. Have you ever wondered about the role neutron stars play in the grand tapestry of the cosmos? Beyond their individual characteristics, these stars are key to understanding the life cycles of galaxies. By studying neutron stars, astronomers gain insight into the processes that govern stellar evolution and the ultimate destinies of stars, including our own sun. It's a humbling reminder of our place in the cosmos. Now, let's delve into something truly extraordinary. Some neutron stars are part of systems known as pulsar planets. These are planets that orbit around pulsars, and the first exoplanets ever discovered were, in fact, orbiting around a pulsar. The conditions on these planets are unimaginable, bathed in the intense radiation and magnetic fields of their pulsar stars. It's a stark reminder of the diverse range of environments in our universe. Speaking of remarkable systems, did you know that certain binary neutron star systems are so intricately bound that they can complete an orbit around each other in less than 2 hours? The strong gravitational interactions in these systems can lead to fascinating phenomena such as gravitational radiation, providing a dynamic playground for astrophysical studies. And here's a delightful tidbit. Neutron stars can also possess a phenomenon known as superfluidity in their interiors. This state of matter allows particles to flow without friction, leading to unique and complex rotational behaviors. It's like having a superconductor deep within a star, adding yet another layer of complexity to these already intriguing objects. Let's not forget the awe-inspiring role of neutron stars in the mystery of missing matter in the universe. Some theories suggest that neutron stars could be repositories of dark matter or exotic particles, potentially holding the secrets to one of the universe's greatest enigmas. It's a tantalizing possibility that keeps scientists eagerly searching for answers. Consider this. The pulsations of some neutron stars are so regular that they rival the accuracy of atomic clocks used here on Earth. These cosmic timekeepers provide invaluable precision for numerous scientific endeavors, including testing the limits of general relativity and improving our understanding of fundamental physics. It's fascinating how the universe offers its own intricate timepieces, ticking away in the vastness of space. As we wrap up this gentle exploration of celestial wonders, imagine the sheer diversity and complexity of neutron stars and pulsars. Each one is a testament to the universe's boundless creativity and power. The more we learn about these enigmatic objects, the more we realize how much more there is to discover. As you drift further into the realm of dreams, let the stories of these stellar marvels inspire your imagination, weaving dreams of distant galaxies and the mysteries waiting to be unraveled. Let your mind wander among the stars, where every new fact is a gentle whisper from the cosmos, inviting you to dream, explore, and discover. As you continue to journey through the world of neutron stars and pulsars, imagine the remarkable phenomenon where some pulsars send out beams of radiation that are so bright they can be detected from thousands of light years away. These beams sweep through space like cosmic lighthouses, illuminating the darkness in periodic flashes that can be precisely counted, much like the ticks of a cosmic metronome. It's astonishing to think that these beams travel across such vast distances to reach us here on Earth. Now, let me share something equally intriguing. Neutron stars are incredibly dense. So dense, in fact, that a sugar cube-sized piece of neutron star material would weigh about as much as all of humanity combined. Imagine holding such a powerful piece of the universe in your hand. A truly mind-bending thought, isn't it? This extreme density is a result of the star's core collapsing under its own gravity, crushing protons and electrons together to form neutrons. Here's something particularly captivating. Neutron stars can spin at an incredible speed, sometimes making several hundred rotations per second. Known as millisecond pulsars, these rapidly spinning stars are among the fastest spinning objects in the universe. They are kept in such rapid rotation by the transfer of angular momentum from an orbiting companion, akin to a cosmic dance that never ceases. Speaking of cosmic dances, did you know that neutron stars can create a gravitational wave symphony when they collide? These waves ripple through the fabric of space-time itself, offering indirect evidence for their existence long before they were directly detected. The collision of two neutron stars is one of the most energetic events in the universe, releasing an astonishing amount of energy, and it can even lead to the creation of heavy elements like gold and platinum in their wake. Consider this remarkable fact. Neutron stars have incredibly strong magnetic fields, which can be over 1 trillion times stronger than the Earth's magnetic field. These fields play a crucial role in the emission of radiation from pulsars and can cause fascinating phenomena like magnetars, which are neutron stars with magnetic fields so strong that they can distort the atoms in their vicinity. Imagine the power contained within such a star, shaping the very atoms that surround it. Have you ever thought about the light-bending capabilities of neutron stars? Due to their immense gravity, they can bend the path of light that passes near them, an effect known as gravitational lensing. This can cause the images of background stars to be distorted or even magnified, offering a stunning view into the interplay between light and gravity in the cosmos. Let's delve into the curious nature of glitching pulsars. Occasionally, some pulsars undergo sudden changes in their rotational speed, known as glitches. These glitches are believed to be caused by a sudden reconfiguration in the star's interior, offering a unique glimpse into the state of matter under extreme conditions. It's as if the star experiences a sudden, brief hiccup, resuming its regular rhythm shortly afterward. There's also the fascinating concept of the pulsar timing array. Astronomers use the regular pulses from multiple pulsars to detect gravitational waves from supermassive black holes. This method turns the entire galaxy into a giant gravitational wave detector, showcasing the incredible ingenuity of scientists in using natural phenomena to probe the universe's secrets. Imagine a star that is so compact it defies the usual rules of star classification. Neutron stars are such objects, so much so that they represent the densest form of matter known outside of a black hole. Speaking of density, have you wondered about the colors of neutron stars? Despite their names, these stars aren't necessarily black or even dark. Some shine with a brilliant blue or white hue, radiating the remnants of their initial energy output. Here's a thought to ponder. In some cases, neutron stars can form during supernova explosions, where the outer layers of a massive star are violently ejected into space. The core that remains collapses into a neutron star, a process that happens in a fraction of a second, leaving behind a dense, rapidly spinning remnant. This is a stark reminder of the transformative power of death and rebirth in the universe. Speaking of rebirth, neutron stars are often located in regions teeming with stellar nurseries, areas rich in gas and dust where new stars are born. Their presence in these regions hints at the continual cycle of destruction and creation that defines our universe. Can you imagine the dynamic life cycles at play, orchestrating the birth of stars from the remnants of their predecessors? And here's an enchanting idea. Neutron stars are thought to be the potential birthplace of certain elements like strontium. When neutron stars collide, the intense conditions can forge new elements, dispersing them across the cosmos. It's a cosmic alchemy occurring on a grand scale, contributing to the intricate tapestry of matter that makes up our universe. Finally, consider the beautiful notion that neutron stars, through their gravitational interactions, can alter the orbits of nearby stars, subtly influencing their paths over vast timescales. This gentle, persistent tug is a reminder of the interconnectedness of all things in the cosmos, a quiet yet powerful testament to the forces that bind our universe together. As you drift deeper into the soothing embrace of sleep, let these astonishing tales of neutron stars and pulsars cradle your dreams. Imagine the swirling dance of stars, the cosmic symphonies of gravitational waves, and the mysterious forces that shape the heavens. Let your imagination soar among these stellar wonders, weaving a tapestry of dreams spun from the very fabric of the universe itself. Imagine for a moment the incredible temperatures at the core of a neutron star. These stellar remnants boast temperatures reaching up to 1,000,000 degrees Celsius right after their formation. Over time, they cool down, but they're still unimaginably hot, glowing fiercely in the infrared spectrum. The cooling process of a neutron star is as fascinating as its formation. Speaking of cooling, did you know that neutron stars can exhibit what's called neutrino cooling? In the first few years of their lives, neutron stars rapidly lose heat by emitting neutrinos, ghostly particles that barely interact with matter. The study of this cooling process helps scientists understand the physics of extremely dense objects and the behavior of matter at the nuclear level. Now, picture this. A neutron star's crust is not like any other. It's composed of a solid lattice of ions, with a density so great that a single sugar cube-sized portion of it would weigh about as much as all of humanity put together. This crust is believed to be incredibly strong, capable of supporting enormous mountains, albeit only a few millimeters high due to the intense gravity. Speaking of gravity, have you ever considered the escape velocity from a neutron star? It's an astonishing number, around 150,000 kilometers per second. That's about half the speed of light. It means anything trying to leave the surface would need to travel at impossibly high speeds to break free from its gravitational pull. And here's a curious phenomenon. Neutron stars are sometimes found in binary systems where they orbit another star. In such cases, they can accrete matter from their companions, leading to the emission of X-rays. These systems are known as X-ray binaries, and they provide a unique opportunity to study the interactions between neutron stars and their companion stars. Let's dive into the concept of starquakes. Just like the Earth, neutron stars can experience quakes that shake their crust. These starquakes are caused by the intense gravitational forces and magnetic stresses at play, sometimes leading to sudden changes in the star's rotation. The study of such quakes can reveal much about the internal structure of neutron stars. Another fascinating aspect is the role neutron stars play in measuring the universe. By timing the regular pulses from pulsars, astronomers can measure the effects of gravitational waves passing between the Earth and the pulsar, making them powerful tools for understanding the universe's expansion and the distribution of matter within it. Did you ever wonder how neutron stars got their name? It's because they are primarily composed of neutrons, with the intense gravitational pressure forcing protons and electrons to combine into these neutral particles. This process creates an object so dense and compact that a single teaspoon of neutron star material would weigh billions of tons. Speaking of density, imagine the pressure within a neutron star. It is so high that it forces atoms to be packed incredibly tightly, resulting in a state of matter that cannot exist under normal conditions. This pressure is key to understanding how matter behaves at such extreme densities, a topic that continues to intrigue physicists. Here's a delightful tidbit. Not all neutron stars are pulsars. For a neutron star to become a pulsar, its rotation and magnetic axis must be misaligned, creating a lighthouse effect where beams of radiation sweep across the sky. If the beam happens to sweep across the Earth, we can detect it as regular pulses of radiation, hence the name pulsar. Don't you find it intriguing that pulsars can be used as cosmic clocks? Their rotations are incredibly regular, making them some of the most precise natural timekeepers known. This precision allows astronomers to test the limits of general relativity and understand the dynamics of binary systems. Speaking of precision, did you know that the first extrasolar planets were discovered orbiting a pulsar? This discovery was unexpected, as the environment around a pulsar is incredibly hostile with intense radiation. Yet, these planets somehow managed to form or survive in such conditions, challenging our understanding of planet formation. Here's something to ponder. Neutron stars have a unique sound, if you will, in the universe. The regular pulses of radiation they emit can be converted into sound waves, allowing us to listen to their rhythmic beats. It's as though the cosmos itself is playing a symphony, with each pulsar contributing its own unique note. Finally, consider the role of neutron stars in the cosmic ecosystem. Their existence and interactions with their surroundings help recycle material in the galaxy, contributing to the formation of new stars and the distribution of elements. They are an essential part of the cosmic cycle, acting as both creators and destroyers in the vast theater of the universe. Let these captivating stories of neutron stars and pulsars fill your mind with wonder as you drift into a peaceful slumber. Picture the immense forces at play, the extraordinary phenomena they inspire, and the fascinating mysteries they hold. Allow your dreams to be guided by the rhythm of the universe, a gentle reminder of the beauty and complexity of the cosmos. Close your eyes and imagine a universe where neutron stars spin with unimaginable speed. Some pulsars, known as millisecond pulsars, rotate hundreds of times per second. Can you picture such dizzying speed? These rapid rotations arise from interactions within binary systems, where the neutron star accretes matter from its companion and gains angular momentum, spinning up like a cosmic skater pulling in their arms. It's a dance of celestial bodies that challenges our sense of time. Let me share another wonder: the magnetic fields of neutron stars. These fields are among the strongest known in the universe. A typical neutron star can have a magnetic field strength trillions of times greater than Earth's. Such intense fields can bend the paths of particles and influence the star's emissions, shaping the beams of radiation we observe. Their enormity touches on the limits of our understanding of electromagnetism. Now, did you know that as neutron stars age, their rotations gradually slow down? This deceleration is due to the emission of radiation and the loss of angular momentum. Yet even as they slow, pulsars remain remarkably precise, their pulses acting like ticking cosmic metronomes. Their constancy offers scientists a window into the passage of time across the universe. Here's a curious tidbit: neutron stars can sometimes merge, creating a spectacular event known as a kilonova. When two neutron stars collide, they release incredible amounts of energy and create heavy elements like gold and platinum. These cosmic crashes are so powerful that they can be seen across vast distances in the universe, leaving a legacy of new materials scattered among the stars. Speaking of cosmic collisions, have you ever wondered about the role of neutron stars in the creation of black holes? When two neutron stars merge, if the resulting mass is sufficiently large, a black hole may form. This transformation from neutron star to black hole is a dramatic event, illustrating the delicate balance of forces at the extreme edges of physics. In exploring these celestial phenomena, we find that neutron stars are not just passive observers of the universe. They are active participants. Some pulsars emit beams of particles that can influence nearby interstellar matter, creating nebulae and complex structures. These emissions weave patterns in the fabric of space, revealing the dynamic interplay between stars and their environments. Here's something to ponder: the concept of pulsar timing arrays. By precisely measuring the pulses from many pulsars, astronomers can detect gravitational waves, ripples in space-time caused by cataclysmic events, like merging black holes. It's a method that turns pulsars into a vast network of cosmic detectors, listening to the universe's most profound disturbances. Doesn't it amaze you that neutron stars can sometimes switch their behavior? Some have been observed to transition between being a pulsar and a magnetar, a type of neutron star with an even stronger magnetic field. This switching behavior provides clues about the internal dynamics and magnetic properties of these fascinating objects, offering a glimpse into their complex lives. Consider the phenomenon of glitches in pulsars. These are sudden increases in a pulsar's spin rate, thought to be caused by shifts in the star's internal structure or the crust's abrupt movements. These glitches offer scientists a rare opportunity to probe the interior of neutron stars, revealing the hidden mechanisms that govern their behavior. In the realm of the unexpected, some neutron stars are known as RATs, or rotating radio transients. These stars emit sporadic bursts of radio waves, unlike the regular pulses of most pulsars. The cause of this erratic behavior remains a mystery, pointing to the diverse and unpredictable nature of neutron stars. And here's another surprise. Neutron stars can have atmospheres, albeit thin and tenuous. These atmospheres are composed of light elements like hydrogen or helium, influenced by the star's intense gravity and magnetic field. The study of these atmospheres can provide insights into the conditions on the star's surface and the processes occurring within. It's intriguing to think about neutron stars in relation to Einstein's theory of relativity. The intense gravity near these stars bends space-time, affecting the path of light and the flow of time. Observations of neutron stars test the predictions of relativity, offering a real-world laboratory for exploring the nature of gravity. Finally, consider the possibility of neutron stars having surrounding disks of debris. In some cases, remnants of material from the star's formation or a companion's destruction can form a disk, influencing the star's behavior and emissions. These disks add yet another layer of complexity to the already multifaceted nature of neutron stars. As you drift further into relaxation, let these surprising aspects of neutron stars and pulsars fill your imagination with awe. Picture the intricate dynamics of their existence, the mysteries they hold, and the cosmic scales they operate on. These celestial wonders serve as a testament to the natural universe's complexity and beauty, a gentle reminder of the vastness that lies beyond our reach. Imagine, if you will, a neutron star twinkling faintly in the night sky, its light reaching you through eons of time and space. These stars, remnants of massive stellar explosions, possess the densest matter in the known universe. Picture this: a single sugar cube-sized piece of neutron star material would weigh about as much as all of humanity combined. Such density is difficult to comprehend, challenging our understanding of matter itself. Here's something else to consider. Neutron stars can emit light across a broad spectrum of electromagnetic radiation, from radio waves to gamma rays. This incredible range allows astronomers to study them using a variety of telescopes, each revealing unique aspects of these celestial objects. The diverse emissions tell tales of their energetic processes, drawing a vibrant picture of their dynamic nature. Did you know that the surfaces of neutron stars are incredibly smooth? Despite their tumultuous formation, the intense gravitational force of a neutron star flattens any surface irregularities, resulting in a surface smoother than any object found on Earth. This smoothness is a stark contrast to the chaotic forces at play beneath their crusts, where extreme pressures and temperatures forge a realm beyond our terrestrial experience. Speaking of their surfaces, neutron stars can sometimes exhibit starquakes, akin to Earth's earthquakes, but on a cosmic scale. These starquakes occur when the crust of the neutron star, strained by its own magnetic fields, suddenly fractures and shifts. The energy released can momentarily alter the star's spin, providing astronomers with valuable insights into its internal structure and magnetic dynamics. And here's a fascinating fact. Some neutron stars may have a companion in the form of a planetary system. Discoveries of planets orbiting pulsars have fueled intrigue about the formation and survival of such systems under extreme conditions. These pulsar planets, despite their harsh environment, pose intriguing questions about planetary formation and the potential for exotic worlds beyond our solar system. Consider, too, the peculiar phenomenon known as pulsar wind nebulae. These are clouds of energetic particles accelerated by the magnetic field and rotation of a pulsar. As these particles move at nearly the speed of light, they illuminate the surrounding nebula, creating spectacular displays that can be observed from Earth. These nebulae offer a glimpse into the high-energy processes at play in the universe, painting the sky with their radiant glow. Here's another curious aspect of neutron stars. Their tremendous gravitational pull can warp space-time around them. This effect, predicted by Einstein's theory of general relativity, is so strong that it can bend light, allowing us to observe parts of the star that would otherwise be hidden. This gravitational lensing effect provides a natural telescope, enabling us to study regions of space that are otherwise inaccessible. Imagine the temperatures on the surface of a newly formed neutron star. These youthful stars can reach temperatures of over 1 million degrees Celsius, radiating intense heat that gradually cools over time. As they age, neutron stars become cooler and dimmer, yet their core remains hot and dense, a testament to the extreme conditions of their creation. And did you know that pulsars can be used as cosmic lighthouses to navigate the vastness of space? Their precise and regular emissions can serve as reference points for spacecraft, offering a celestial GPS system that could guide future interstellar travel. The thought of using neutron stars as navigational beacons truly highlights their utility beyond scientific exploration. In a surprising twist, some neutron stars possess glory halos, a kind of optical illusion caused by light bending around the star. These halos can appear when conditions are just right, creating an ethereal visual effect that captivates the imagination and underscores the beauty of these distant objects. Speaking of beauty, have you ever wondered about the colors of neutron stars? Though often depicted as blue or white due to their high temperatures, neutron stars can exhibit a range of colors depending on their temperature and magnetic activity. This spectrum of colors enriches our understanding of their properties, adding another layer to their multifaceted nature. There's also the phenomenon of precession in some neutron stars, where the star's rotation axis gradually shifts. This motion can alter the orientation of the star's emission beams, leading to changes in the observed pulse profile. This subtle dance of motion provides clues about the star's internal and external dynamics, revealing the complexities of their rotational behavior. Let's not forget the concept of neutron star binaries, where two neutron stars orbit each other in a cosmic waltz. These pairs, when they finally merge, offer a unique opportunity to study the laws of physics under extreme conditions. The gravitational waves produced by such mergers ripple through space, providing insights into the fabric of the universe itself. Finally, ponder the idea that neutron stars may harbor exotic states of matter, like quark-gluon plasma or even strange matter. These theoretical states challenge our understanding of particle physics, suggesting that neutron stars could be laboratories for testing the fundamental laws of the universe. Such possibilities enrich our knowledge and spark our curiosity about the nature of existence, As you drift further into relaxation, let your mind wander through these incredible facts about neutron stars and pulsars. Their stories, etched in the fabric of the cosmos, invite us to explore the wonders of the universe with awe and reverence. Let me share with you a surprising fact about neutron stars that might intrigue your imagination. Did you know that despite their incredible density, neutron stars rotate at astonishing speeds? Some can complete a full rotation in just a few milliseconds. These millisecond pulsars are among the fastest spinning objects in the universe. This rapid rotation is a remnant of their formation process, where a collapsing star retains its angular momentum, spinning faster as it shrinks. Imagine a cosmic ice skater pulling in their arms to spin faster, and you'll have a sense of what these stellar remnants are doing. Speaking of their rotation, have you ever wondered about the forces at play inside a neutron star? One fascinating theory suggests the presence of nuclear pasta, a term used to describe the unique shapes formed by nuclear matter under extreme pressure. These structures, named for their resemblance to pasta shapes like spaghetti and lasagna, are thought to exist in the crust of the neutron star. This peculiar arrangement of matter could help explain some of the star's magnetic and thermal properties. Now, let's turn our gaze to another intriguing feature. Neutron stars can host incredibly strong magnetic fields, sometimes billions of times stronger than any magnetic field we can create on Earth. These fields are so intense that they can disrupt atoms and molecules, influencing the star's behavior and interactions with its surroundings. Magnetars, a type of neutron star with even more powerful magnetic fields, can emit bursts of X-rays and gamma rays as these fields shift and rearrange. And here's something you might find interesting. Neutron stars can occasionally consume material from a companion star. This process, called accretion, involves the neutron star's gravity pulling in gas and dust from a neighboring star. As this material spirals inward, it forms an accretion disk that heats up and radiates X-rays, offering a window into the dynamics of stellar interactions. Have you ever thought about how neutron stars communicate? Some pulsars emit radio waves in a regular pattern, much like a lighthouse beacon. These signals, when received on Earth, provide astronomers with precise timing measurements that can test theories of gravity and even detect gravitational waves. The reliability of these pulses makes pulsars some of the most precise clocks in the universe, with certain pulsars maintaining timing accuracy over millions of years. Now consider the energy contained within a pulsar. Imagine harnessing the rotational energy of just one of these celestial bodies. The energy released by a single pulsar could outshine our sun by a factor of 100,000, providing a glimpse into the incredible power stored within these remnants of stellar evolution. Here's a curious fact. The interiors of neutron stars remain largely mysterious. While we can learn about their surfaces through telescopic observations, the core of a neutron star is inaccessible. The extreme conditions make it a challenging but fascinating subject for theoretical physics, as scientists attempt to simulate the interior conditions using powerful supercomputers and advanced models. Did you know that neutron stars can act as cosmic laboratories for testing the laws of physics? The conditions within these stars are so extreme that they allow scientists to explore states of matter not possible on Earth. In this realm, the boundaries of known physics are pushed, offering potential insights into the behavior of matter at nuclear densities. Imagine the neutron star's role as a cosmic recycler. When a star explodes in a supernova, it releases elements into space which later become the building blocks for new stars and planets. Neutron stars, as remnants of these explosions, play a part in this ongoing cycle of creation and destruction, reminding us of the interconnectedness of all cosmic phenomena. And let's not overlook the fact that neutron stars can sometimes merge with black holes. This cosmic dance can result in the emission of gravitational waves, rippling through space-time and offering us a way to observe these extraordinary events. The merger of such dense objects also poses questions about the ultimate fate of the matter involved, challenging our understanding of both neutron stars and black holes. As you ponder these facts, let your curiosity wander to the realms of neutron stars and pulsars, where the universe's most extreme phenomena unfold. These celestial objects are not just remnants of stellar death, but are gateways to understanding the complexities of the cosmos. Their stories continue to inspire awe and wonder, inviting us to unravel the mysteries of our universe with each new discovery. Embrace the calm of this shared journey through the stars as we explore the beauty and intricacy of neutron stars and pulsars together. Let me take you on a journey where we unravel more about these cosmic marvels. Did you know that neutron stars are incredibly small in comparison to their mass? Imagine this: taking a mass greater than that of our Sun and compressing it into a sphere with a radius of just around 10 kilometers. It's like fitting a mountain into a teacup, only much more extreme. The crushing gravitational force on the surface is so immense that if you were to drop a marshmallow from a meter above, it would hit the surface with the force of 1,000 nuclear bombs. Here's something else to pique your interest. Neutron stars are not always solitary travelers of the cosmos. Some exist in binary systems, where their interactions with companion stars lead to fascinating phenomena. As they orbit one another, the gravitational dance can result in the emission of gravitational waves, ripples in space-time that we can detect here on Earth. These waves offer us a glimpse into the dynamics of these extraordinary systems. Speaking of companions, neutron stars can also be part of a system known as a pulsar wind nebula. This happens when the powerful winds from a pulsar collide with surrounding material, creating a glowing nebula. The intricate beauty of these nebulae, visible through telescopes, is a testament to the dynamic interactions occurring in these distant regions of space. Have you ever wondered about the environments around neutron stars? They can become incredibly energetic places. The intense magnetic fields and rapid rotation of pulsars can accelerate particles to near-light speeds, creating beams of radiation that sweep across space. When these beams point towards Earth, we detect them as pulsating radio signals, giving pulsars their name and making them cosmic lighthouses. Let me share another captivating insight. Neutron stars can experience starquakes. Much like earthquakes on Earth, starquakes occur due to the rigid crust of a neutron star cracking and shifting. This can cause sudden changes in the star's rotation rate, a phenomenon known as a glitch. These glitches provide clues about the internal structure of neutron stars, as well as the forces at play within them. In the realm of neutron stars, time behaves in unusual ways. Due to their massive gravity, time on the surface of a neutron star runs slightly slower compared to time experienced far away from the star. This effect, known as gravitational time dilation, is a prediction of Einstein's theory of general relativity, and is yet another example of how the extreme conditions around neutron stars can test the limits of our understanding of physics. Now, consider the role of neutron stars in the grand tapestry of the universe. They are thought to be the source of some of the universe's heaviest elements, such as gold and platinum. When neutron stars collide, they can produce kilonovae, immense explosions that not only generate gravitational waves, but also forge these precious elements, enriching the cosmos with their bounty. Some spacecraft are equipped with sensors that can detect pulsar signals, allowing them to determine their position in space with incredible precision. It's a cosmic GPS, guiding explorers through the vastness of space using the steady rhythm of pulsars. Here's another delightful fact. The names given to pulsars often hint at their characteristics. For example, the Crab pulsar, located in the remnants of a supernova observed on Earth in the year 1554, is named for its association with the Crab Nebula. The pulsar's rapid rotation and intense magnetic field power the nebula, creating a spectacular display of energy and light. Imagine this. Inside a neutron star, the density is so high that atomic nuclei are squeezed together to form a sea of neutrons. This state of matter is unlike anything we can produce on Earth, making neutron stars natural laboratories for studying nuclear physics under extreme conditions. The mysteries hidden within their cores continue to challenge our understanding of matter itself. Have you ever thought about the possibility of life around neutron stars? While the conditions seem inhospitable, some scientists speculate about the existence of planets orbiting neutron stars. These hypothetical planets, should they exist, would endure extreme environments, but could hold clues to the resilience and adaptability of life in the universe. In the world of pulsars, timing is everything. The regularity of pulsar signals is so precise that they have been used to test the stability of fundamental physical constants over long periods. Any variation in these constants could indicate new physics beyond our current theories, making pulsars a vital tool in the quest to understand the universe. And here's a thought to ponder. Neutron stars remind us of the cyclical nature of the cosmos. From their violent births in supernovae to their roles as sources of heavy elements and gravitational waves, they are both the end and a new beginning in the cosmic story. As we peer into the depths of space, neutron stars serve as beacons of knowledge, guiding us through their mysteries with each twist and turn of discovery. Allow your mind to drift with these thoughts, as the wonders of neutron stars and pulsars invite you to explore the universe's most profound secrets. Amidst the serenity of the night sky, let these celestial objects whisper their tales, drawing you into the eternal dance of the cosmos. Imagine the universe as a vast symphony, with neutron stars playing an unexpected yet essential melody. Did you know that neutron stars are born from the explosive death of a massive star? When a star many times the mass of our Sun exhausts its nuclear fuel, it undergoes a supernova explosion, leaving behind a dense core. This core, if not massive enough to form a black hole, becomes a neutron star, a remnant packed with more mass than our Sun, yet compressed into a sphere only about 20 kilometers across. Here's something truly remarkable. The gravity on the surface of a neutron star is incredibly strong, about 200 billion times that of Earth's gravity. If you were to stand on a neutron star, the gravitational pull would be so immense that it would instantly flatten you. This extreme gravity is what keeps the star's dense matter from flying apart, maintaining its compact nature. Speaking of immense forces, have you ever heard of magnetars? These are a type of neutron star with magnetic fields so powerful they can disrupt electronic devices from thousands of kilometers away. The magnetic field of a magnetar is 1 trillion times stronger than Earth's magnetic field. When these magnetic fields shift or crack, they can produce giant bursts of X-rays and gamma rays, lighting up our universe in a spectacular display. And here's a fascinating insight. Neutron stars are among the fastest spinning objects in the universe. The fastest known neutron star, or pulsar, completes over 700 rotations per second. This rapid spin is a result of the conservation of angular momentum, a principle that means as the core of the star collapses, it spins faster and faster, much like a figure skater pulling in their arms. Let me share something unexpected. Neutron stars can have atmospheres, albeit incredibly thin ones. These atmospheres are only a few centimeters thick and are composed of hydrogen, helium, or carbon depending on the star. Despite their thinness, these atmospheres play a crucial role in the star's thermal emissions, affecting how we observe them. Have you ever wondered about the colors of neutron stars? While they might seem like distant points of light, neutron stars can actually emit a range of colors, depending on their temperature. A young, hot neutron star can appear blue or white, while an older, cooler one might show red hues. This spectral variation provides astronomers with clues about the star's age and cooling process. Another intriguing thought: some neutron stars are part of what are called millisecond pulsars. These are pulsars that have been spun up by accreting material from a companion star, achieving incredibly fast rotations. The precision of their timing is so reliable that they are used to keep time more accurately than atomic clocks. Did you know that some neutron stars emit not just radio waves, but also X-rays and gamma rays? These emissions come from the acceleration of particles along magnetic field lines, and they offer a different window into the physics of neutron stars. Observing these high-energy emissions allows scientists to study the magnetic fields and surface conditions of these enigmatic stars. Speaking of emissions, neutron stars can also flicker in brightness, known as glitches. These sudden changes in a pulsar's rotation rate can cause variations in the timing of their pulses. Glitches are thought to result from shifts in the star's superfluid interior or the breaking of its crust, providing insights into the extreme physics governing their interiors. Here's something to imagine. Neutron stars can have hot spots on their surfaces, regions much hotter than the surrounding areas. These hotspots occur where the magnetic field lines converge, concentrating energy and heating the surface. As the neutron star spins, these hotspots can cause variations in the star's light curve, much like a rotating lighthouse beam. Have you ever considered the role of neutron stars in gravitational astronomy? The study of their gravitational wave emissions from binary systems is a burgeoning field that allows scientists to test theories of gravity and explore the properties of dense matter. These waves carry information about the masses and orbital dynamics of the stars, expanding our understanding of the universe's fundamental forces. In the realm of neutron stars, even the smallest detail can hold a universe of information. Did you know that the crust of a neutron star is believed to be one of the strongest materials known? This crust, composed of densely packed nuclei, is estimated to be 10 billion times stronger than steel. Understanding its properties helps scientists learn more about nuclear interactions under extreme pressures and densities. Imagine the concept of glitches in a different light. Some neutron stars experience anti-glitches, where they suddenly slow down instead of speeding up. This phenomenon is rarer and not well understood, but it adds another layer of complexity to the already fascinating behavior of neutron stars. Let us ponder for a moment the notion of a death spiral. When two neutron stars in a binary system lose energy through gravitational waves, their orbits decay, bringing them closer together in a spiraling dance. Eventually they merge in a cataclysmic event, producing a burst of gravitational waves and possibly forming a black hole. These events offer a unique glimpse into the extreme conditions present during such powerful cosmic collisions. And finally, consider the tantalizing possibility that neutron stars might harbor exotic states of matter deep within their cores, where temperatures and pressures are beyond anything else in the universe. It's possible that quarks, the fundamental building blocks of matter, could exist freely. This hypothetical quark matter remains a mystery that scientists are eager to unravel, as it could redefine our understanding of matter itself. May these musings on neutron stars and pulsars lull you into a state of cosmic wonder as the mysteries of the universe continue to unfold before your imagination. Let us journey further into the captivating world of neutron stars and pulsars. Imagine, if you will, the immense densities of these stars. A single sugar cube-sized amount of neutron star material would weigh as much as a mountain on Earth. This incredible density is a result of their formation process, where the core of a massive star collapses under gravity, squeezing matter into an unimaginably small volume. Here's something that might surprise you. Neutron stars are incredibly hot. When they are newly formed, they can have temperatures reaching several 100 billion degrees Celsius. Over time they cool, but even then, their temperatures can remain around 1,000,000 degrees, keeping them as some of the hottest objects in the universe. Despite their intense heat, these stars are so compact that their energy output is not as great as you might expect. Speaking of compactness, a neutron star is so small that it would easily fit within the boundaries of a city. Imagine a star with a mass greater than that of our Sun, squished into a sphere with a diameter of only about 20 kilometers. This compactness leads to their incredible gravitational pull, which is so strong that if you were to drop something from just 1 meter above the surface, it would hit the ground at about 7 million kilometers per hour. Did you ever wonder how we know so much about these distant objects? Pulsars, a type of neutron star, provide us with cosmic lighthouses, beaming regular pulses of radiation that can be detected by telescopes on Earth. The regularity of these pulses allows scientists to study the timing with incredible precision. In fact, timing these pulses has led to the discovery of thousands of pulsars throughout the galaxy. And here's another intriguing thought. Some pulsars are located in globular clusters, dense collections of stars that orbit the galaxy's core. These environments are perfect for forming millisecond pulsars because of the frequent stellar interactions that can lead to the spinning up of neutron stars. The dense star fields within these clusters provide rich hunting grounds for astronomers seeking these fascinating objects. Let's consider the role of neutron stars in the cosmic recycling process. When a neutron star forms, it is the core remnant of a supernova explosion. This explosion disperses heavier elements into space, enriching the cosmos with materials necessary for the formation of new stars and planets. In this way, neutron stars are pivotal in the cycle of cosmic evolution, helping to shape the universe as we know it. You might be surprised to learn that some neutron stars are known as magnetars, which have magnetic fields so powerful that they can distort atomic structures and molecules even at a considerable distance. These magnetic fields are 1,000,000 times stronger than those of typical neutron stars and can affect space itself, altering the dynamics of charged particles in their vicinity. Here's a curious fact. Because of their incredible density, neutron stars have an extraordinary ability to bend light. This phenomenon, known as gravitational lensing, means that light from stars behind a neutron star can be bent around it, creating a distorted image. Observing such effects helps astronomers study the properties of extreme gravity and the nature of space-time. And consider this. Neutron stars can emit beams of particles at nearly the speed of light. These jets are typically found in systems where the neutron star is drawing material from a companion star. As the material spirals into the neutron star, it heats up and produces X-rays, while the spinning magnetic field funnels particles along the poles, creating powerful beams. Did you know that the study of pulsars has even contributed to testing Einstein's theory of general relativity? In binary systems where two neutron stars orbit each other closely, their movements and the gravitational waves they produce can provide precise tests of general relativity, confirming its predictions with remarkable accuracy. And speaking of gravitational waves, neutron-star collisions are one of the few sources of these ripples in space-time that we can observe. When two neutron stars merge, they send out gravitational waves that can be detected by instruments like LIGO and Virgo. These detections not only confirm theoretical predictions, but also open new windows into the study of the universe's most extreme phenomena. Have you ever thought about the possibility of planet-like bodies orbiting neutron stars? Indeed, some neutron stars do have planets, known as pulsar planets, which were the first planets discovered outside our solar system. These planets likely formed from the debris left over after the neutron star's formation or were captured by the star's gravity later on. Here's one more enigma. Neutron stars are incredibly efficient at converting matter to energy. The gravitational energy released by the infall of matter onto a neutron star's surface is much more efficient than nuclear fusion in stars like our Sun. This efficiency makes them some of the brightest X-ray sources in the universe, even if only for short periods. And finally, consider that within the confines of a neutron star, the laws of physics are pushed to their limits. The extreme conditions challenge our understanding of matter and energy, making neutron stars natural laboratories for exploring fundamental physics. They provide us with a unique opportunity to test the boundaries of our scientific knowledge, encouraging both awe and curiosity about the universe's most mysterious objects. As you drift into a peaceful slumber, let these remarkable aspects of neutron stars and pulsars inspire dreams of the cosmos and the endless wonders it holds. In the vast expanse of space, the mysteries of neutron stars and pulsars continue to captivate us. Imagine, for example, that neutron stars are so dense that a sugar cube-sized amount of their material would weigh about 6 billion tons on Earth. This density is almost unimaginable, yet it highlights the extraordinary nature of these celestial objects. Speaking of their surprising characteristics, did you know that some neutron stars can spin incredibly fast? These are known as millisecond pulsars, which can rotate hundreds of times per second. It's as if these stars are cosmic figure skaters, pulling their arms in tight to increase their spin rate. Interestingly, the surface of a neutron star is not only incredibly dense, but also incredibly smooth. The immense gravitational force effectively flattens any irregularities, creating a surface smoother than the most polished marble. And consider this, even though these stars are so compact, their gravitational influence is immense. If a neutron star were to replace our Sun, its gravity would be so intense that it would distort the orbits of the planets, likely pulling them into its destructive embrace. Have you ever wondered about the temperatures on a neutron star? The core can reach temperatures of over 1 million degrees Celsius shortly after its formation. However, these stars cool rapidly over time, radiating their heat into the cosmos. Despite this cooling, the surface temperature remains scorching for a long time, maintaining remarkable levels of thermal radiation. And here's another mind-boggling detail. Neutron stars have an outer crust of solid and incredibly dense matter, yet beneath this crust lies a fluid of neutrons, behaving almost like a superfluid with no viscosity. You might be intrigued to learn that timing the regular pulses of pulsars has enabled astronomers to create an incredibly precise cosmic clock. These pulsar clocks are so accurate that they can rival atomic clocks on Earth, enabling scientists to measure time with exceptional precision. And speaking of precision, pulsars have also been used to help navigate spacecraft. By triangulating the signals from multiple pulsars, spacecraft can determine their positions in the vastness of space, much like a cosmic GPS system. The magnetic fields of pulsars are another source of wonder. Can you imagine a magnetic field so strong that it could erase credit card information from 1,000 kilometers away? This powerful magnetism is not just a curiosity, it plays a critical role in the generation of pulsar wind nebulae, which are glowing clouds of charged particles surrounding some pulsars. These nebulae emit X-rays and other forms of high-energy radiation, contributing to the complex dynamics of the surrounding space. Here's something curious. The study of neutron stars can even provide insight into nuclear physics. The extreme conditions within these stars mimic those found in atomic nuclei, offering a natural laboratory where scientists can test theories about the behavior of matter under such intense pressure and density. This connection between the cosmos and the fundamental components of matter on Earth is a testament to the interwoven nature of the universe. Did you know that some neutron stars can exhibit starquakes? Just like earthquakes on Earth, these starquakes occur when the crust of a neutron star suddenly shifts, releasing immense energy. The energy from these quakes can momentarily increase the star's brightness, allowing astronomers to study these powerful events from afar. Consider the gravitational waves produced by neutron star interactions. When neutron stars spiral towards each other and eventually collide, they create ripples in space-time. These gravitational waves travel across the universe, carrying information about the cataclysmic events that birthed them. Detecting these waves has opened an entirely new way to observe the universe, allowing scientists to peer into regions otherwise hidden from view. And here's a charming idea. Some neutron stars are part of binary systems, orbiting with a companion star. In such systems, the neutron star can draw matter from its companion, creating an accretion disk around itself. The friction and heat from this disk can lead to bursts of X-ray emission, which are among the brightest in the universe, albeit fleeting. Another fascinating aspect is the potential for neutron stars to host exotic states of matter. Deep within their cores, beyond the superfluid neutrons, there might exist a state of matter called quark-gluon plasma. This is a condition where quarks and gluons, the building blocks of protons and neutrons, exist freely in a way that cannot be replicated in any laboratory on Earth. Have you ever imagined the life cycle of a pulsar? As they age, pulsars tend to slow down and emit less radiation. Eventually, they become so weak that they can no longer be detected, fading into obscurity. This gradual decay is akin to a cosmic heartbeat, slowly winding down over millions of years. And finally, consider the role neutron stars play in enriching the universe. When they form, the supernova explosions that give birth to them scatter elements across space, providing the raw materials for new stars and planets. This process of cosmic seeding ensures that neutron stars, despite their daunting nature, contribute to the cycle of star formation, bringing life to the cosmos in their own unique way. As you close your eyes and let these thoughts drift through your mind, imagine the silent dance of neutron stars and pulsars echoing through the universe and leaving trails of wonder in their wake. It's fascinating to think about the immense density of neutron stars, Imagine compressing the entire mass of the Sun into a sphere with a diameter of just about 20 kilometers. The resulting object would have such a gravitational pull that if you were to drop a marshmallow onto its surface, it would hit with the energy of 1,000 atomic bombs. This brings to mind another incredible fact. The speed required to escape the gravitational grip of a neutron star is close to 1/3 of the speed of light. Can you picture that? It's a speed beyond anything we can currently achieve with our technology. Speaking of astonishing numbers, did you know that neutron stars possess rotational speeds that can boggle the mind? Some pulsars rotate hundreds of times per second, so fast that they can complete a revolution in the time it takes you to blink. This rapid spinning creates a centrifugal force stretching the star outward. Despite this, the star's gravity is so strong that it maintains its shape. Here's an intriguing thought. Neutron stars can be incredibly magnetic. Some of them, known as magnetars, have magnetic fields 1,000 times stronger than that of a typical neutron star. These fields are so intense that they can distort atomic structures at a distance of thousands of kilometers. The resulting electromagnetic radiation can be so powerful that it causes starquakes, with reverberations felt across incredible distances. Interestingly, neutron stars can emit beams of radiation from their magnetic poles, which, when aligned with Earth, are detected as pulses. This lighthouse effect is what characterizes pulsars. In their youthful stage, these pulses can be extraordinarily precise, rivaling the accuracy of the best atomic clocks. This precision has allowed scientists to use pulsars as cosmic lighthouses, navigating the vast expanse of space. And here's a charming tidbit. Some pulsars are part of binary systems with another star. As the neutron star siphons material from its companion, the infall creates spectacular X-ray emissions, providing a fireworks show that can be observed across the universe. This process is not only mesmerizing, but also critical for studying the behavior of matter under extreme conditions. The idea that neutron stars might contain exotic forms of matter is truly captivating. Beyond the superfluid neutrons, there is speculation that the core might contain free quarks and gluons, behaving unlike anything we can produce on Earth. This exotic state is a realm of physics that remains largely theoretical, yet neutron stars offer a glimpse into these tantalizing possibilities. A curious fact is that the gravitational field of a neutron star is so intense that it can bend the light coming from its surface. This gravitational lensing means that more than half of the star's surface can be visible at once, giving it a unique appearance. This phenomenon offers astronomers a way to study the star's properties more comprehensively. In some instances, neutron stars can be ejected from their birthplace at extraordinary speeds. These runaway neutron stars, sometimes referred to as cannonballs, travel through the galaxy at speeds reaching up to 1,000 kilometers per second. Such velocities make them some of the fastest objects in the universe, with their paths charted by traces of radiation left behind. One might wonder how these stars form in the first place. Neutron stars arise from the remnants of supernova explosions, when the core of a massive star collapses under gravity. This collapse is so rapid and intense that it crushes electrons and protons into neutrons and neutrinos. The resulting neutron star is an ultra-dense remnant, a stellar core stripped to its most fundamental components. Amidst these cosmic wonders, did you know that the study of neutron stars has even influenced our understanding of fundamental physics? Insights gained from neutron stars have implications for nuclear physics, particularly in understanding the behavior of matter under extreme pressure and density. This cross-disciplinary influence showcases the interconnectedness of cosmic phenomena and terrestrial science. Remarkably, the energy output of a pulsar can be enormous despite its small size. Some pulsars emit more energy in a single second than the Sun does in an entire year. This prodigious output is primarily in the form of radiation and high-energy particles, a testament to the incredible power locked within these compact stars. Here's another fascinating aspect. Neutron stars can host planets. Although rare, some pulsars have been found with planets orbiting them. These planets, formed from the debris of a supernova, offer a glimpse into planetary formation in environments vastly different from our own solar system. And let's not forget the impact of neutron stars on their surroundings. Their strong magnetic fields and radiation can influence nearby space, potentially triggering the formation of new stars and planets. This capacity to shape their environment highlights the dynamic nature of neutron stars within the cosmic tapestry. Finally, consider the longevity of these stars. Despite their initial brightness and activity, neutron stars can persist for billions of years. Over time, they cool and slow, becoming faint whispers of their former selves, yet their influence lingers, continuing to enrich the universe for eons to come. As you drift into slumber, let your mind wander through the vastness of space and time, where neutron stars and pulsars spin silently, their mysteries patiently awaiting our discovery. These celestial wonders not only illuminate the night sky, but also light the path to understanding the universe's deepest secrets. May your dreams be filled with the gentle hum of the cosmos, guiding you to realms of infinite possibility and wonder. Imagine gazing deep into the universe, where neutron stars, these celestial enigmas, continue to capture our curiosity. Did you know that the surface of a neutron star is not smooth but rather has towering mountains? These mountains are not like those here on Earth, but instead they are mere centimeters high due to the immense gravitational forces. Yet, in the realm of neutron stars, these tiny protrusions are significant enough to generate gravitational waves as the star spins. These ripples in space-time are faint whispers of the star's dynamic nature and contribute to our understanding of the universe's structure. Speaking of structure, neutron stars have incredibly thin outer crusts, just a couple of kilometers thick, enveloping a superfluid interior. This superfluid is a state of matter that flows without friction, enabling the interior to rotate independently from the crust. Imagine, if you will, a dense, massive sphere with an outer shell that moves at a different rate than its core. This phenomenon leads to fascinating differential rotation effects, providing insight into the star's interior dynamics. Here's something to ponder. Despite their extreme density, neutron stars are also characterized by their incredibly rapid spin. Some of these stars, known as millisecond pulsars, can rotate hundreds of times per second. This rapid spin is due to the conservation of angular momentum from their progenitor stars, meaning as the star shrinks, it spins faster, much like an ice skater pulling in their arms during a spin. These dizzying rotations offer astronomers a natural laboratory to study the laws of physics under the most extreme conditions. As you imagine these rapidly spinning stars, consider this. The pulse rate of some pulsars can change dramatically. On occasions, these stars experience a sudden increase in rotational speed, referred to as a glitch. These glitches might be caused by the interaction between the crust and the superfluid core, leading to sudden shifts and adjustments in the star's rotation. This phenomenon is not only intriguing, but also vital for understanding the internal mechanics of neutron stars. Now, let's look at the effect of a neutron star on its immediate surroundings. Picture a neutron star traveling through the interstellar medium. As it moves, it creates a bow shock, akin to the wake of a ship. This shock wave compresses and heats the surrounding gas, sometimes resulting in a glowing arc observed by astronomers. These bow shocks are not just beautiful, they provide crucial data about the interstellar medium and the star's velocity. Speaking of velocity, consider the neutron star's incredible speed. Some are moving so fast that they are being ejected from their galaxies. These hypervelocity stars are flung into the vastness of space, potentially becoming intergalactic wanderers. Their journeys across the cosmos challenge our understanding of gravitational interactions and stellar dynamics, reminding us of the universe's vast scale. Did you know that neutron stars can form in clusters? These clusters, often found in the dense cores of globular clusters, pose an interesting puzzle. The stars within these tightly packed regions can interact gravitationally with one another, resulting in dynamic and occasionally violent encounters. These interactions could lead to the formation of exotic systems, such as binary pulsars, or even the rare occurrence of neutron star mergers. A merger of neutron stars is a spectacular event that releases enormous amounts of energy, often observed as short gamma-ray bursts. These cataclysmic collisions not only provide insight into the properties of dense matter, but also play a crucial role in the creation of heavy elements like gold and platinum. The alchemy of the cosmos, bringing forth elements that enrich the universe, is a direct result of these dramatic stellar interactions. And here's another thought-provoking fact. Neutron stars exhibit a phenomenon known as frame dragging, predicted by Einstein's theory of general relativity. The intense gravity of a rotating neutron star warps space-time around it, dragging the fabric of space along with its spin. This effect, though incredibly subtle, has been measured in some systems, offering a tantalizing glimpse into the complex interplay between gravity and rotation. Consider the light emitted by these stars. Neutron stars can exhibit a wide spectrum of radiation, from radio waves to X-rays. The spectrum of a neutron star reveals much about its temperature, magnetic field, and rotation speed. In some cases, the star's extreme magnetic field can polarize the light, offering clues about the magnetic field structure and the environment immediately surrounding the star. Another fascinating aspect is the possibility of neutron stars having atmospheres, albeit incredibly thin ones. Composed mostly of hydrogen or helium, these atmospheres are only a few centimeters thick, yet they influence the thermal radiation emitted by the star, affecting how we observe them from Earth. This thin veil of gas is a testament to the complex interactions taking place even in such extreme environments. Finally, in the enigmatic dance of matter and energy, neutron stars can be sources of intense bursts of gamma rays. These bursts, called magnetar flares, are one of the most powerful explosions in the universe, releasing in just a fraction of a second more energy than the sun emits in 100,000 years. The exact mechanism behind these flares remains a mystery, continuing to puzzle and inspire astronomers worldwide. With each revelation about neutron stars and pulsars, we are reminded of the universe's vast and multifaceted nature. These stellar remnants, both powerful and mysterious, offer a window into the fundamental processes that govern our cosmos. As you drift into dreams, envision these cosmic sentinels spinning through the night, silent guardians of the universe's deepest secrets. Let their stories inspire a sense of wonder and curiosity as vast as the night sky itself. Imagine, if you will, a neutron star's magnetic field. It's a force of nature so intense that it can be over 1 trillion times stronger than Earth's own magnetic field. This staggering strength can actually affect the surrounding space and have a profound impact on the behavior of particles nearby. Did you know that in such a powerful magnetic environment, the very laws of physics as we understand them can behave differently, causing electrons to move in unusual ways? This showcases how neutron stars can become natural laboratories for studying extreme physics. Speaking of magnetic fields, consider this. Some neutron stars, known as magnetars, have fields that are even more intense. These fields are so powerful that they could erase the magnetic strip on a credit card from hundreds of thousands of kilometers away. The energy stored in a magnetar's magnetic field is mind-boggling and can lead to dramatic events such as starquakes on the star's crust, releasing enormous amounts of energy. Here's a curious thought. Neutron stars are not only about force and magnetism. Some are partnered with other stars in binary systems, leading to fascinating interactions. As the neutron star pulls material from its companion, it can form an accretion disk. This disk is a swirling maelstrom of gas and dust, heated to millions of degrees, emitting X-rays that can be detected from Earth. The dynamics of these disks provide insight into the interactions between stars and the movement of matter under extreme conditions. And consider this intriguing scenario. If two neutron stars are in a binary system, they can spiral towards each other over millions of years, eventually colliding in a spectacular merger. Such an event not only produces gravitational waves, ripples in the fabric of space-time, but also releases heavy elements into the cosmos. This cosmic dance and eventual union play a crucial role in the synthesis of elements and the enrichment of the universe. Switching perspectives, let's talk about the neutron star's crust. This crust, while only a few kilometers thick, is one of the strongest and most dense materials known. To put it into perspective, a sugar cube-sized piece of neutron star crust would weigh as much as Mount Everest. The study of this crust can provide valuable information about nuclear interactions and the behavior of matter at densities far beyond what we can replicate on Earth. Now, here's an interesting tidbit. Beneath the crust lies the neutron star's core, where the density is so high that atomic nuclei are crushed together, and protons and electrons combine to form neutrons. This environment creates a superfluid core, a state of matter that flows without viscosity. This superfluidity affects the star's rotation and leads to the fascinating glitches we mentioned earlier. Reflecting on their origins, neutron stars are born from the remnants of supernova explosions. These cataclysmic events occur when a massive star exhausts its nuclear fuel and collapses under its own gravity. The core's collapse is halted by neutron degeneracy pressure, resulting in a neutron star. This transformation from a massive, bright star into a dense, compact neutron star is a journey of dramatic change, a phoenix-like rebirth from the ashes of a stellar giant. Thinking about their life cycle, not all neutron stars remain solitary. Some evolve into pulsars, which emit beams of radiation like cosmic lighthouses. These beams, if aligned with Earth, can be detected as regular pulses. The rotation period of pulsars can be incredibly consistent, rivaling atomic clocks in precision. This precision allows astronomers to use pulsars as natural tools for testing the laws of physics under conditions we cannot recreate on Earth. Here's another intriguing aspect. Neutron stars are incredibly small given their mass. Typically, they are only about 20 kilometers in diameter, yet they can contain more mass than our Sun. This compactness means that if you were to stand on the surface of a neutron star, you would weigh millions of times more than you do on Earth. This immense gravity would flatten anything on the surface to a sheet of atoms, a testament to the power of gravity at such scales. And there's the phenomenon of pulsar timing. Observations of pulsars can help us detect objects otherwise invisible to our telescopes, such as exoplanets orbiting neutron stars. The gravitational effects of these planets can cause slight changes in the pulse timing, revealing their presence. This method has already led to the discovery of planets in the most unlikely of places and continues to expand our understanding of planetary systems. Lastly, let's turn to the role neutron stars play in our understanding of the universe. Besides being fascinating in their own right, they also serve as beacons, helping astronomers map the galaxy. The precise timing of pulsar signals allows us to measure distances within the Milky Way accurately, painting a clearer picture of our cosmic neighborhood. As we drift into the realm of dreams, let these stellar phenomena ignite your imagination. Each neutron star, like a cosmic storyteller, shares tales of energy, physics, and cosmic drama, inviting us to ponder the universe's grand designs. Through their stories, we find ourselves both humbled and inspired by the wonders of the cosmos. Imagine, if you will, the gravity of neutron stars. Not only does it hold unimaginable mass within such a compact sphere, but it also bends light around it, creating a gravitational lensing effect. This means that if you were observing a neutron star, you would be able to see the light from its far side, an optical illusion born from the warping of space-time itself. Speaking of illusions, did you know that the surface of a neutron star is so smooth that it rivals polished metal? Despite their violent births and the incredible forces at play, the surface irregularities are no more than a few centimeters high, quite remarkable when you consider the forces involved in their formation. Furthermore, there's something extraordinary about the speed at which these stars can rotate. Some neutron stars, known as millisecond pulsars, can spin hundreds of times per second. To put it in perspective, the fastest known pulsar rotates over 700 times each second. This rapid spinning is a reminder of the immense energy that these compact objects contain. And here's an interesting tidbit. As pulsars age, their rotation slows down. However, if a pulsar is part of a binary system, accreting material from a companion star, it can be spun up again to these incredible speeds, essentially rejuvenating itself. Continuing on this theme of rejuvenation, did you know that the magnetic fields of neutron stars can also evolve over time? Initially, these fields are incredibly strong, but they do decay gradually over millions of years. Under certain circumstances, this decay can cause the star to emit enormous bursts of energy, known as soft gamma repeaters. These bursts are a reminder of the latent power residing within these celestial objects. And speaking of power, the energy emitted by a pulsar in just 1 second can exceed the energy output of our Sun over 1 million years. Here's something that might surprise you. Neutron stars are not all about overwhelming power and force. Some have complex layered structures beneath their solid crusts, with a mantle composed of superfluid neutrons. This mantle flows in a way that can affect the star's rotation, leading to sudden changes known as glitches. These glitches provide a window into the mysterious internal processes that govern the star's behavior. Let's shift focus slightly. The study of neutron stars has also led to the discovery of a unique state of matter known as color superconductivity. This exotic phase occurs at the core of the neutron star, where quarks, the building blocks of protons and neutrons, exist in a free state. Understanding this state of matter may unlock secrets about the universe's earliest moments, just after the Big Bang. Can you imagine that the gravity of a neutron star is so intense that it can actually slow down time? This time dilation effect, predicted by Einstein's theory of general relativity, means that time moves slower on a neutron star than it does on Earth. If you were able to visit a neutron star and then return to Earth, you would find that more time had passed here on Earth than for you. There's another curious phenomenon associated with pulsars. They can act as natural particle accelerators. The intense electromagnetic fields surrounding a pulsar can accelerate particles to speeds approaching that of light. These high-energy particles are responsible for a variety of cosmic rays that we detect on Earth. Speaking of detection, pulsars are also crucial in the ongoing search for gravitational waves. As they orbit in binary systems, they emit gravitational waves that can provide critical information about the nature of gravity itself. Now, let's explore the concept of pulsar wind nebulae. When a pulsar emits a powerful wind of charged particles, this wind can create a nebula around the pulsar, visible in X-rays and radio waves. These nebulae are complex and dynamic, offering insight into the high-energy processes occurring around pulsars. One of the most intriguing aspects of neutron stars is the possibility of discovering quark stars. These hypothetical stars would be even denser than neutron stars, composed entirely of quark matter. Though yet to be observed, quark stars would challenge our understanding of matter under the most extreme conditions. Another fascinating point to ponder is the role of neutron stars in the cosmic balance. As they collide and merge, they contribute to the synthesis of heavy elements like gold and platinum, enriching the universe and playing a part in the cosmic cycle of matter. In this way, neutron stars are not only remnants of stellar deaths, but also seeds of new beginnings. Finally, consider the vast distances over which pulsars can be detected. Despite their small size, the beams of radiation they emit can be observed from across the galaxy, serving as cosmic beacons that help map the vast expanse of the Milky Way. These signals traverse the cosmic ocean, carrying with them tales of their origins and the secrets of the universe. As we reflect on these incredible facts, it is clear that neutron stars and pulsars are not merely astronomical objects, but gateways to understanding the cosmos on both grand and minute scales. Through their silent yet powerful presence, they continue to inspire wonder and curiosity, inviting us to explore the mysteries of the universe. As you drift into a restful slumber, let the thoughts of these cosmic wonders accompany you into the night, sparking dreams of the vast, intricate dance of the stars above. Let me share something intriguing with you. Neutron stars, despite their compact size, can possess masses up to 2 times that of our Sun. Imagine that, an entire sun compressed into a sphere only about 20 kilometers in diameter. This incredible density is why neutron stars are often referred to as one of the universe's strangest objects. Now, let's delve into their fascinating magnetic properties. Neutron stars exhibit magnetic fields that are trillions of times stronger than Earth's own magnetic field. These intense fields can distort the space around the star, a mind-boggling concept when you consider the force required to warp the very fabric of space. Here's something that might surprise you. Neutron stars are incredibly efficient in converting gravitational energy into radiation, making them some of the most luminous objects in the universe relative to their size. As a neutron star accretes material from a companion star, this process can release bursts of X-rays, lighting up the cosmos with their radiant energy. And speaking of light, did you know that the surface of a neutron star is so hot that it emits predominantly X-rays? The surface temperature can soar up to several million degrees, a stark contrast to the relatively cool temperatures we are accustomed to here on Earth. Transitioning to another intriguing aspect, consider how neutron stars can serve as cosmic lighthouses. Their regular pulsations, caused by their rapid rotation and magnetic field alignment, make them highly precise timekeepers. In fact, some pulsars rival the accuracy of atomic clocks, providing a natural standard for measuring time. This precision has even been utilized in navigating spacecraft through the cosmos, a testament to the utility of these distant celestial objects. Did you know that neutron stars can have crusts that are 10 billion times stronger than steel? This incredible strength is due to the intense pressure and density, creating a material known as nuclear pasta. Despite its delicious-sounding name, nuclear pasta is among the toughest materials in the universe. It's fascinating to think about how these extreme conditions can give rise to such peculiar physical states. Another remarkable fact is that neutron stars can exhibit a phenomenon known as glitches, where their rotation becomes suddenly faster. These glitches are thought to occur due to the interactions between the star's crust and its superfluid interior. This peculiar behavior offers insights into the complex and dynamic nature of neutron stars, providing clues about the exotic states of matter that exist within them. Let's turn our attention to the role neutron stars play in the grand tapestry of cosmic events. When two neutron stars collide, they can create a spectacular explosion known as a kilonova. These events are not only breathtakingly beautiful, but also crucial for the creation of heavy elements. During these cataclysmic mergers, elements like gold and platinum are forged, enriching the universe and contributing to the elemental diversity we observe today. Here's something to ponder. Neutron stars can host entire planetary systems. Some pulsars have been found with planets orbiting them, remnants of the star's original planetary system, or newly formed from the debris of the supernova explosion. These pulsar planets are often exposed to intense radiation, making them inhospitable by earthly standards, yet their existence challenges our understanding of planetary formation and survival in extreme conditions. And consider this: neutron stars are not just solitary wanderers. They are often found in binary systems, where their interactions with a companion star can lead to fascinating phenomena. For instance, the gas from a companion star can be pulled onto the neutron star, creating an accretion disk that emits powerful X-rays. This process is a dazzling display of celestial dynamics at play, revealing the complex interactions between these stellar remnants and their neighbors. Have you ever wondered about the possibility of neutron stars merging to form a black hole? Such dramatic events occur when the combined mass of two neutron stars exceeds the threshold for black hole formation. The gravitational waves emitted during these collisions provide a wealth of information about the properties of matter under extreme conditions, opening new windows into the study of gravity and relativity. Finally, let's consider the role of neutron stars in advancing our understanding of fundamental physics. These stars are natural laboratories for testing the limits of our physical theories, especially in the realm of quantum mechanics and general relativity. Their study has the potential to reveal new physics, pushing the boundaries of our knowledge and offering glimpses into the universe's most profound mysteries. As we explore these astonishing facts about neutron stars and pulsars, it's clear that they are not just lifeless remnants of stars, but vibrant and dynamic entities that challenge and expand our understanding of the cosmos. Their complex behaviors and extreme conditions serve as a reminder of the beauty and wonder that exist in the universe. As you close your eyes and drift into sleep, let these cosmic wonders fill your dreams, guiding you through the vast and mysterious universe that surrounds us. Neutron stars, these incredible remnants of stellar evolution, continue to captivate astronomers and dreamers alike with their enigmatic properties. One of the most surprising things about neutron stars is their rotational speed. You might be amazed to learn that some neutron stars spin incredibly fast, completing a full rotation in just milliseconds. These are known as millisecond pulsars, and their rapid pace is comparable to the speed of a kitchen blender. Can you imagine something with the mass of a sun rotating so quickly? Speaking of pulsars, did you know that they can emit beams of radiation that sweep across the cosmos like cosmic lighthouses? These beams are so regular that when they were first discovered, scientists considered the possibility that they might be signals from intelligent extraterrestrial life. Of course, they are natural phenomena, but it's intriguing to think about the initial excitement they caused. Now, here's a curious thought. Neutron stars are so dense that a single teaspoon of neutron star material would weigh as much as a mountain. This incredible density is due to the immense gravitational forces acting on the matter within the star, compressing it to unfathomable extremes. The concept of holding a mountain's worth of weight in a tiny amount of material stretches our imagination about what is possible in the universe. Another fascinating aspect is how neutron stars can act as cosmic laboratories, revealing extraordinary states of matter. Hidden within their cores might exist an exotic form known as quark-gluon plasma, a state theorized to have existed just moments after the Big Bang. This plasma consists of elementary particles like quarks and gluons, free from their usual confinement within protons and neutrons. Imagine peering into the earliest moments of the universe by studying the heart of a neutron star. And here's something unexpected. Neutron stars have been found with extremely strong magnetic fields, known as magnetars. These magnetic fields are so intense that they can strip atoms of their electrons and even distort the shapes of atomic nuclei. If you were near a magnetar, its magnetic field would be strong enough to distort the atoms in your body. Such power is difficult to comprehend, but it highlights the extreme physics that neutron stars can display. Have you ever thought about how neutron stars can actually slow down over time? This gradual slowing is due to the loss of energy as they emit radiation into space. However, the process is not always smooth. Occasionally, neutron stars experience a sudden speed-up or glitch, as previously mentioned. These glitches can offer insight into the inner workings of the star, much like an astronomical puzzle waiting to be solved. Here's an intriguing fact. Neutron stars can sometimes emit giant flares of gamma rays, among the most energetic events known in the universe. These flares can be so powerful that they affect the Earth's atmosphere, even from thousands of light years away. It's a humbling reminder of the immense energies at play far beyond our own planet. Speaking of energies, have you ever considered how neutron stars can gravitationally affect nearby objects in space? Their strong gravitational pull can warp time and space around them. This warping has implications for the movement of stars, planets, and even light itself. A beam of light passing close by would follow a curved path, illustrating the profound effects of gravity on the fabric of the universe. Let's delve into the interaction between neutron stars and black holes. When a neutron star merges with a black hole, it produces gravitational waves that ripple through the cosmos. These waves carry information about the star's masses and spins, offering a window into their mysterious nature. The detection of such waves has opened new avenues for astronomical discovery, allowing us to listen to the universe in an entirely new way. And here's a delightful surprise. Neutron stars can actually be quite social. They sometimes occur in clusters, often in the bustling environments of globular clusters, dense collections of stars packed closely together. The presence of neutron stars in these clusters suggests that their formation and evolution might be influenced by their stellar neighbors, adding another layer of complexity to their story. Have you ever wondered how neutron stars can contribute to the cosmic alchemy of the universe? As they collide and merge, the extreme conditions can forge elements heavier than iron, enriching the interstellar medium with materials that eventually become part of new stars, planets, and even life itself. This process of stellar recycling is crucial for the chemical evolution of galaxies, ensuring the continued diversity of elements. Finally, while neutron stars might seem distant and detached from our everyday experience, they are deeply connected to the cosmic web of life. The elements produced in their fiery births and explosive ends find their way into the building blocks of life, bridging the gap between the distant stars and the molecules that make up living organisms. As you drift into sleep, imagine the intricate dance of neutron stars, their stories written in the starlight we see, their mysteries whispered through the cosmic winds. Let their wonders fill your dreams as you wander through the vast and mysterious tapestry of the universe, where every star has a story to tell and every pulsar sings a song of time and space.